Okay, so like I said, we're going to continue on lecturing here a little bit. Keeps on pace. Spring break next week, they say. So so close. Um, any questions on what we talked about so far? So we've talked about last time here the common ion effect on solubility, and again, it's a negative effect in most cases on solubility, as it will again keep the salt together, not allow it to break apart as much as it usually will, and will decrease the solubility. The next sort of thing that we're going to talk about in terms of sort of an effect on solubility is pH and solubility. So the presence of a common ion, as we just saw, will decrease the solubility of a salt. Uh, the pH is also a really big factor in terms of solubility, and that's why, for example, when you do like your group 1 and some point, I guess we'll do group 3, group 4, qualitative analysis sort of experiments. Again, there's a lot of steps where you sort of adjust the pH of your solution. And really, the goal of that, as we talked about, is to allow certain ions to remain in solution because they're going to be less soluble or more soluble in that pH environment, and some will be less soluble and they'll come out of solution. So we have insoluble bases will dissolve in acidic solutions, and insoluble acids will dissolve in basic solutions. So, for example, here, if we look at sort of a base action going on here with magnesium hydroxide, and again, the KSP value there, 1.2 times 10 to the minus 11. And as you can see there, if we write our KSP expression, which would be our magnesium and our hydroxide squared. Now, if we wanted to sort of go through our KSP sort of table here, we would have 0 and 0. We will have plus S, and again here plus 2S because of the coefficient. That will get us here S and 2S, if I wrote the S there. And that will go into our KSP expression here, which will give us S times 2S squared is equal to our KSP value 1.2 times 10 to the minus 11. That's going to be something for S cubed, I think, is equal to 1.2 times 10 to the minus 11. Now, if we want to solve for the molar solubility here of this solution, we're going to divide by 4 and then come back through and take the cube root of it. So we'll take 1.2 to the minus 11 divided by 4. That's going to give us S cubed is equal to 3 times 10 to the minus 12. Taking the cube root there, once again, if you don't have a button to do that, you can caret it, and 1 divided by 3 will do that cube root for you. And we will get a molar solubility here of, we'll call it 1.4 times 10. 1, 2, 3, 4, minus 4 molar. Now, since we are talking about pH here, um, it would make sense that perhaps our hydroxide would be of interest there in terms of the pH. And that's because it'll get us to the POH. So if I do want the hydroxide concentration, as we can see from our ice table, it's actually 2 times S. So we do need to pop that in there. And that will get us here, when we go higher here, our hydroxide is 2 times S, which would be 2 times our 1.4 times 10 to the minus 4. And that's going to get us here 2 times 1.4 to the minus 4. A hydroxide concentration of 2.8 times 10 to the minus 4. Because we now have the hydroxide concentration, we can now calculate the POH of this solution. POH of the solution would be minus the log of 2.8 times 10 to the minus 4. So minus the log of that there. Going to give us a POH of 3.55. That then means we can just subtract 14 here to get to our pH. And that means approximately here we are looking at a 1045 pH for this solution. So 1045 sort of the baseline pH of this solution. It's kind of where it's sitting. It is basic, which is good because that's kind of a base. So that's a basic pH. First off, any question on that calculation there? So it's kind of like we talked about at the very end last time. In these cases where you maybe have something with hydroxide in it, maybe you have something with H plus or H3O plus, you can actually get the pH of that sort of salt solution. And here it is 10.45. So why is that number important? That number is important because that's like the baseline pH of the solution, which means let's say here that I decided to lower the pH less than 10.45. So let's just say I want to take the solution now and I want to kind of drop the pH there less than 4.45. How would I lower pH? I probably is going to be adding what to it? To lower pH, you would add a acid, which is essentially meaning that you are going to be adding H plus, right? And what's going to happen when I add that H plus is not part of this equilibrium, right? But H plus is probably attracted to what thing? It is attracted to the hydroxide, right? Because those two guys are then going to make water, right? And because that is then going to basically make water, that is essentially doing what to my hydroxide here? That is essentially going to be removing my hydroxide from this equilibrium. And because it's removing my hydroxide from this equilibrium, Le Chatelier's principle is going to tell me it's going to shift which way, to the left or to the right. It's going to shift towards the side we're removing, which means it is going to shift to the right. And that means, will I have more solid or less solid in this case? I will have less solid. And that's what the first sentence, actually, that's what the second sentence says up there. First sentence, insoluble bases will dissolve in acidic solution. So when we drop the pH of this and we add that acid to it, it is essentially going to be removing the hydroxide from that equilibrium. It's going to cause the equilibrium to shift to the right, and we actually will see more of this guy start to dissolve. Do I need to get it to an acidic pH to actually see that happen? The answer is no. You just need to drop it below that 10.45 number. It'll still be basic and it will start to dissolve more as you drop the pH. So that's why calculating that number of 10.45 is kind of important, because you know kind of where you're starting. As long as you even drop it less than that, even if it's still basic, but it's a lower pH, you are going to see that effect happening. You are going to see it to start to dissolve. And obviously, as you continue to do that, you'll see more and more of it to dissolve. Now, what would happen in the opposite case here is if we decided, well, let's just say I want to increase my pH above 10.45. In order to increase my pH, I would most likely need to add, in this case, a base, which essentially means I am adding hydroxide in this case. That means that I'm going to add some hydroxide to this equilibrium when I'm doing that. And we do see hydroxide in the actual equilibrium. So that would essentially mean that I'm going to be adding more products in this case, right? Which means the equilibrium then will shift away towards the reactants in this case. Would I expect more of it to dissolve or less of it to dissolve? Actually, more solid form. You will actually start to see more solid form, because you're going to cause the rest of those guys floating around and now decide to jump out of solution and head over there and become a solid. So in this case, we're adding more OH minus. It's going to cause to shift equilibrium, and it's really going to decrease the solubility. So again, this is why, for example, when you do those qualitative analysis experiments and you're changing the pH from acidic to basic, basic to acidic, all in the same sentence, the purpose of that, again, is going to allow certain ions to remain in solution. It's going to allow other ions to be able to precipitate out of solution. This is also why, for example, maybe you did it in group one, when you added acid, for example, and it wasn't acidic enough, I think they told you, hey, test it on litmus or a pH paper to make sure it's at least a pH of 2 or whatever it was, 1. And the reason for that is if you don't get it acidic enough, you won't see the precipitate come out. And this is also why, in certain cases, if you're not careful when you're doing experiments like that, and you're not careful about the pH of your solution, when you should see a precipitate come out, you may not see it because the pH is not right. So, pH plays a really big role, especially with insoluble acids and bases, as to whether or not you will see sort of a precipitate come out or not. And it also is, for example, when you talk about qualitative analysis, group two, which we don't do anymore, group three, they both are precipitated out with hydrogen sulfide gas or sulfur. But the difference between them is actually the pH of those things. One is very acidic, and that allows group three to stay in solution and not come out. And then you turn it to really basic, and then allow group three ions to come out of solution. So although they're using the same sort of reagent to precipitate out, if you had both of those together, by changing the pH, that's going to be enough to keep one in solution and allow the other group to come out of solution. Any questions on pH and solubility here? Okay. Now, lastly, we talked now about common ion and effect on solubility. We just talked about pH on the effect of solubility. The other major thing that is important in terms of solubility, and for example, whether or not you will see a precipitate form, is actually the concentration of your ions. And if you do not have the right concentration of ions, you may not see a precipitate happen, even though our solubility rules say when you throw these two things together, you should get a solid. If you don't really have the right concentration of those ions, you may actually not be able to see it. So this is where we could use Q versus the KSP. And remember that Q, once again, is calculated the same way as the KSP. And if Q is greater than the KSP, a precipitate will occur. So again, if you think about the equation solid to aqueous ions, again, opposite of where that is pointing, when Q is on the left, it means you're going to go to the left there and you should expect a solid. If Q is less than K, that's going to go opposite of that, and you would expect no precipitate to form as it goes to the right. So let's try one here and see. So why don't you try it here? If I take 2 milliliters of a 0.2 molar sodium hydroxide solution and I add it to 1 liter of a 0.1 molar calcium chloride solution, will a precipitate form? In case you're not sure, your ions floating around are sodium ions, hydroxide ions, calcium, and chloride ions. The first thing you would want to do is figure out, is there anything that will make a solid? Clearly, sodium is not going to do it when it switches because sodium is soluble in everything, which means these guys are not going to make it. And that leaves us really these two guys that will make a solid. We know that because we do have a KSP value here, so we know that's going to make a solid. So why don't you give it a go here, calculate Q, and see if you expect. Okay, so let's take a look. So in this case, we do want to compare the Q to the KSP to see if we would expect to precipitate to form. Solubility rules tell us that when these two guys come together, we should expect to precipitate to form. So really here, we want to think about our Q, and our Q in this case is going to be the concentration of calcium and the concentration of hydroxide. And once again, we do need to square it, as it is basically the same thing as this. And that comes from our calcium hydroxide, which will essentially break apart into a calcium ion and a couple of hydroxide ions here. And again, that is where the squaring part of it comes from. So really, in order to calculate Q, we want the concentration of each of these ions when they're dumped together, basically. So when they're mixed together. And to do that, we should do a little M1 V1 equals M2 V2 action on this. I got my volume in different units. So what I'm going to do is just kind of convert my 1 liter into 1,000 milliliters. That way they're both volumes are in the same units. You could go to liters on both. It doesn't really matter. So obviously here our sodium hydroxide is the source of my hydroxide in this mixture. And my calcium chloride is the source of the calcium in this mixture. That means that the concentration of hydroxide here would be our M1, which is 0.2 molar, times our V1, which is 2 milliliters, equals our second molarity there, which is after they're mixed together. And after they're mixed together here, that looks like we have a total volume of 1,000 milliliters plus 2 milliliters. That's 1,002 milliliters. 1,002 milliliters. That's going to give us a concentration for hydroxide of 0.2 times 2 divided by 1,002. And we'll go with the 3.99 times 10 to the minus 4 molar. Any questions on that? Once again, you could do it in liters if you like on both of those. We also want to get the concentration of calcium. And in this case, it will be 0.1 molar. And then for the calcium, we're going to use 1,000 milliliters of it. And M2, and again, 1,002 milliliters when they're all mixed. That is going to give us a molarity here of something. And do that there. 9.98 times 10 to the minus 2 molar. By the way, again, sodium hydroxide, when it breaks apart into a sodium ion and a hydroxide ion. And it is a 1-to-1 relationship, which means if this guy's concentration was 0.2 molar, the hydroxide is also going to be 0.2 molar. So that's how we know the hydroxide was 0.2 molar. And same thing with our calcium chloride. When our calcium chloride breaks apart, we get a calcium ion and 2 chloride ions. And it is a 1-to-1 relationship between those two. So if this guy was 0.1 molar, the calcium would be 0.1 molar as well. So because they are, again, a 1-to-1 relationship. Now that we have basically our concentrations when we put them together and mix them, we could go into our Q expression here. And our Q expression then would be our calcium, which was 9.98 times 10 to the minus 2 times our hydroxide. And I'm going to go below it because I'm a little out of room there. 3.99 times 10 to the minus 4. We got to make sure we do square it as well. And that's going to get us there times 3.99 to the minus 4 squared. 1.6 for our K times 10 to the minus 8. Any questions on that calculation there? So now that we have our Q and our KSP, our Q value is to the minus 8. Our KSP is actually to the minus 6. That means in this case, our KSP is actually larger, right, than our Q value. Remember, when you have a negative exponent, the smaller negative exponent is the larger number. That means that technically this is going to shift equilibrium to the right, and to the right is aqueous ions. Should we expect to precipitate in this case? The answer is no precipitate in this case because Q is less than the KSP. So this is again a demonstration that although solubility rules tell us that if we throw these guys together, we should get a solid, because our concentration of our ions are not correct to allow us to see the solid, we will not get the solid to form. So those are three really big factors that affect solubility: the concentration of the ions floating around, the pH of the solution, and any presence of common ions. All three of those things can have effect on the solubility of any type of salt that you may come across. Any questions on any of that there? Yeah. Let's talk about another sort of aspect of KSP, which is very helpful and really sort of what you're doing, for example, when you do those qualitative analysis sort of experiments. And this is the idea of sort of selective precipitation. And the idea of this is we could actually use the KSP to our advantage to figure out, if we wanted to precipitate out an ion and keep perhaps another ion still floating around in the solution, what concentration of that precipitating reagent would we have to add to get a precipitate to form? So, for example, in this problem here, we have a beaker, and in this beaker, we have bromide ions floating around, we have chloride ions floating around, and those guys are in a concentration of 0.02 molar. We want to actually precipitate these guys out by basically adding silver ions to it. And as we know from our solubility rules, bromides, chlorides are soluble in everything except silver, right? Lead 2 and mercury 1. So by adding silver here, we want to precipitate out these ions. But we actually want to do it in a selective way where we are going to precipitate out only the silver bromide in this case. And we want to leave the chloride ions still floating around. Now, if you do this not carefully and you grab some silver, like some silver nitrate, for example, and you toss it in there, the problem that will occur is you may get everybody precipitating out all at once. And one of those is silver chloride, and one of them is silver bromide. They're essentially both white solids that occur. And there'll be no way for you to go, well, I think this little grain of white solid is the silver chloride. I think maybe this one is the silver bromide. There really would be no way for you to distinguish between the two. You just know that you maybe got everybody to jump out of solution at once. So we could use KSP to our advantage to figure out how we should precipitate these guys out. That's going to leave, in this case, the chloride ion still floating around. But when we add that silver, it's going to grab only the bromide ions and come out in my example here as blue, even though it'll be more of a white solid in this particular case. So if we look at silver bromide, which has a KSP value of 7.7 times 10 to the minus 13, and I write my KSP expression for this like we saw earlier, this would be the silver concentration times the bromide concentration, and that equals KSP, which is 7.7 times 10 to the minus 13. Now I'm interested in really how much silver I would need to do this. So I could rearrange this expression and actually solve for the silver ion, and that would equal our KSP value of 7.7 times 10 to the minus 13 divided by the concentration of my bromide ions. I actually know the concentration of my bromide ions in this particular example as they gave it to me, which means I could actually put that in there and go 7.7 times 10 to the minus 13 divided by 0.02, which again is our concentration of bromide that's floating around. It's also our concentration of chloride. And if we do that there, 7.7 to the minus 13 divided by 0.02, will give us a 3.9 times 10 to the minus 11 molar as our silver concentration that is needed. So, what does that number represent? That number represents the minimum amount of silver that you need to put in there to start to see silver bromide to basically come out of solution and to start to precipitate out. You got to get your silver concentration to that number or greater, and you will start to see it basically precipitate out as silver bromide. So, we could also do a similar calculation here for silver chloride. We could write our KSP, which would be our silver ion times our chloride ion here, and this equals 1.6 times 10 to the minus 10. Once again, if I solve for silver, 1.6 times 10 to the minus 10 divided by the chloride concentration, and again, it's the same concentration as the bromide, and this will give me here 8 times 10 to the minus 9 molar. That represents the minimum concentration that you need to start to see silver chloride to basically come out. Which one is a lower concentration of silver? The one for silver bromide or the one for silver chloride? It is the one for silver bromide, right? You only need to get it to the minus 11. So, what you would do in this particular case is you would have a silver concentration that is greater than 3.9 times 10 to the minus 11 molar, but it would need to be less than this number because that is the number where we start to see silver chloride start to precipitate out 8.0 times 10 to the minus 9 molar. So if you were going to do this, what you would do is get your silver concentration to 3.9 times 10 to the minus 11, and you could keep increasing if you like, and you should start to see some silver bromide coming out. Really, you'll see some white solid coming out, and you can feel very confident that what you're seeing is silver bromide. Maybe you add it and no more comes out, so you increase the concentration of silver, maybe more precipitate comes out. You could continue to increase the concentration of the silver ion as long as you keep it under 8 times 10 to the minus 9. At some point, hopefully all the bromide will stop precipitating out, and you can feel really confident that you have completely precipitated out all of the bromide ions from that solution. At that point, it would then be safe to beef up your silver concentration to 8 times 10 to the minus 9, and you should once again start to see solid come out. But in this case, the solid should be the silver chloride, as that should be the only ion left in the solution at this point. And you can continue to precipitate out the silver chloride or the chloride as silver chloride. So, although they are again both using the same reagent, the silver, to precipitate out, by controlling the concentration of the silver, you can selectively grab out one ion from the solution and keep the other one still in the solution. Any questions on that? The reason why they say we want to take the silver bromide out first is when we look at silver bromide, that is a total of 2 ions. When we look at silver chloride, that is a total of 2 ions, which means in this particular case, you can compare the KSP values of both of those things. And what we see here is the silver bromide has the smaller KSP value of the two, which means it should be less soluble than the silver chloride. That is why we would attack the silver bromide in this case first, because it's going to come out of solution a lot easier than the silver chloride because of the KSP value here. So KSP is very useful in things like that, which is essentially, like I said, what qualitative analysis experiments are. You're really selectively precipitating out ions from the solution. And by knowing these things, you can control the concentration of your precipitating reagent. And you can, again, just basically selectively precipitate out those ions one at a time. Any question on that calculation there? And speaking of qualitative analysis, we did group 1. It seems like forever. I don't think we're doing group 2 anymore. I think we will do 3 and these guys, I think. Remember, as we talked about when we talked about qualitative analysis, again, these groups are separated out by really solubility factors and the relationship of which things are soluble in these things. As we know here, this is pretty much our solubility of chloride, bromide, and iodide. These are the 3 exceptions. These are our group 2s, our group 3s, and our 4s. As we also talked about precipitating reagents for the group, HCl's we used in group 1 because they will all come out as chlorides. As I mentioned before, group 2 and group 3 actually use the same one, which is sulfides. And the difference here, as we just talked about, is the pH of those guys. One's very, very acidic, like 0.5 pH acidic in group 2, and one's very, very basic when you get to group 3. Again, the difference in that pH is going to allow group 3 to stay in the solution while you're precipitating out group 2, and then you can switch it to basic, which will then take group 3 out of the equation. Typically, when you get down to these guys here, as you will find out, it's a lot of flame test action happening there. There are some that will still make some solids in group 4, but things like sodium and potassium, a little flame test, ammonium, some gas sort of test with some litmus paper. That's clearly what you look like as you're doing these experiments as well. There's some flame test action as well. Any questions on KSP? Yeah. All right, so now we're going to talk about another K value because frankly, we don't have enough. And this is going to be our KF. And KF is the formation constant here. And these are for complex ions and complex ion equilibrium. A complex ion is essentially a metal that's surrounded by a bunch of molecules or ions, which are known as ligands. Ligands are Lewis bases, and you remember Lewis bases. Those are things that do what? Accept, donate, one of those two. Donate a pair of electrons. Yes. So that is a Lewis base. A Lewis acid will accept a pair of electrons because they are electron deficient. They're positive. So Lewis bases are guys that have a pair of electrons to donate, and things like chloride, which is obviously negatively charged, which means it has extra electrons. Things like water, it's also very good. It has non-bonding electrons and polar. Things like ammonia is also a really good Lewis base, also a polar molecule, has non-bonding electrons on the nitrogen if you were to draw the Lewis structure. So here we have cobalt and our 4 chlorides coming together to make our complex ion here, which in a later chapter you will know how to properly name that guy. And this will give us a equilibrium constant, which is known as Kf. And it's just like any other equilibrium constant. It is products over reactants here. Kf values, unlike KSP values, are actually really large values. So KSP values are really small values. Typically speaking, KF values are typically very large values, like really large values. And that means that as the KF value increases, the formation of a complex ion is basically stabilized and wants to happen. So in this case, what we got going on is a cobalt, and directly attached to this cobalt is 4 chlorides. And cobalt here has a +2 charge. And with those 4 negative charges there, gives us an overall -2 charge in this case. Again, these chlorides, because they are negatively charged, are good Lewis bases in this case. They're able to do it to our cobalt, which is basically electron deficient because it's positively charged. So it wants to accept those things. Typically, metals in the middle of complex ions are transition metals, which kind of large charges, +2s, +3s are a lot of times what you see in there. sometimes aluminum as well. Now, by the way, these ligands like chloride, for example, actually do come on one at a time. So they don't actually just all pop on all at once. It is a stepwise sort of formation that occurs, kind of like how hydrogens are lost. So the first thing that would happen is the CO would just pick up one chloride and give us COCl plus. And there actually can be a K value for this first guy here. The next thing that would happen is the COCl plus will then pick up another chloride and make COCl2. And again, you could have an equilibrium for this. Then the COCl2 will pick up another chloride and give you COCl3 minus. And lastly here, this COCl3 minus will pick up a fourth chloride to give us our COCl4 2 minus in this case. Yeah. So ligands actually do come on basically one at a time. They actually set up an equilibrium as they're coming on. And if I took all these reactions together and I added them together, this would cancel, right? Opposite sides. That would cancel opposite sides. That would cancel opposite sides. That would leave me on the left-hand side, one cobalt and 1, 2, 3, 4 chlorides. Gives me my complex ions. So what we're looking at in the above equation is really the overall reaction that's happening after all the ligands come together. By the way, if I want to calculate my Kf, what do I do with all those K values? I do what? We do multiply them, right? So we do not add. So it would be K1 times K2 times K3 times K4 in this case. So remember that when you add together equations, equilibrium equations, we actually multiply the K values to get the overall K value in this particular case. Any questions on that there? All right, so KFs are specifically for complex ion formation. They are typically really large values, which means, frankly, when you have the opportunity to make a complex ion, get out of its way. That's what's going to happen. It's going to want to make a complex ion pretty much. So let's take a look at what we do with these type of problems, which might be a little bit different than how we approach some other problems. But a couple other things before we get there. As I mentioned before, some very common ligands, which are Lewis bases, water, ammonia, fluoride, cyanide. Again, water having those non-bonding electrons on the oxygen. Nitrogen there in our ammonia also has the non-bonding electrons and is polar, which is really good. Another thing that we sometimes talk about when we look at complex ions is what is known as the coordination number. And the coordination number is basically how many atoms are directly attached to the metal in the complex ion. So for example, here, if we have our cobalt with our water, it would be the oxygen in this case attaching. And directly attached to that is 1, 2, 3, 4, 5, and 6, which is the coordination number, which is 6. Now, sometimes people mistakenly think it's always going to be the little coefficient there, or not really coefficient, subscript there. It is in both of these cases, and that is because there are different types of ligands, as we'll talk about in a later chapter, There are certain ligands like water, like ammonia, like chloride, which are known as being monodentate, which means for every one of those molecules, they basically only attach in one spot, like through the oxygen here, or just through the chloride. But there are also some ligands which are sometimes referred to as being bidentate. For example, our friend oxalate here looks something like this, I think. Something like that. So this is oxalate, which is a bidentate ligand, which means that if you hooked up oxalate, for example, with a metal, you're going to get a 2-for-1 deal here. You're going to actually have two atoms attaching to the metal per every oxalate molecule, which means if I had two oxalate molecules, and they will attach through the single bonded oxygen there that has a negative formal charge. The coordination number here will actually be 4 in this case. And when you look at the formula, it may have the metal and your oxalate and a 2 down here. But the coordination number will actually be a 4 because you get like a 2-for-1 deal on that guy. 2 atoms combined for every one of those that comes in contact. So just for this point in this chapter here, just think about that it will not always necessarily be the little subscript that is there. Sometimes it will be if it's monodentate, but it can be a different number. And we'll see more of that a little bit later on in a different chapter. All right. So let's take a look at this problem here together and talk about how we should approach sort of KF problems, which is a little bit different than some other problems. We're going to assume here in this particular case that everyone has a constant volume of 1 liter. So again, that's not always the case, but to just sort of keep the numbers not too bad here, we're just going to assume that everybody has just 1 liter as their total volume. So we're going to mix 0.2 moles of copper 2 sulfate with 1 liter of 1.2 moles of ammonia. We want to know what is the concentration of copper 2 in this particular case. So in this case, we're going to get the concentrations here of our copper 2, and that is going to come from our copper 2 sulfate. And in this particular case, it's going to be 0.2 molar, as we're going to assume 1 liter. So 0.2 moles divided by 1 liter, and everybody's just going to be 1 liter. It's going to keep us at 0.2. The ammonia obviously is going to come here, which we're just going to assume is also that molarity as well in this case. So we're going to do an ice table here. So initially for our copper, we have 0.2. And for our ammonia here, we have 1.2. And we have nothing going on here for our complex ion. We could obviously also write our KF expression, which is our products, our CuNH3 divided by our copper 2 and our NH3, which we do need to take to the 4th power because of the coefficient that is there. Now, one of the assumptions that we make when we do a KF type problem is when we look at the KF value here, as I mentioned before, that number is a really large number to the 13, basically a giant K value, considering that 1 is considered a large value. So to the 13 is a really large value. So because it's a really large value, the assumption that we make in these type of problems is everybody is going to the right-hand side. So all of that metal in this case is going to find itself tied up in that complex ion because of the really large value of K. Everybody's going this way. And this is going to be kind of like our limiting reagent in this case. All that is going to get used up. So slightly different than some ice tables that we've done before. We kind of already know what the change is going to be. And in this case, it's actually going to be the metal. We still have to take into account our stoichiometry and everything like we normally would do in an ice table. So what I'm going to do is first do the ice table here in red, the change part, like if we were going to do it with x's. And if we were going to do it with x's, this would be minus x, right? This would be minus 4x, and this would be plus x, right? If we were going to throw x's. We actually don't really need to throw the x's in there because we already know what the x is, and it's going to be the actual metal. So what you could do in this case is not do the red part, and you will do it in blue. You could go minus 0.2, which is basically what x is equal to. You could do minus 4 because of the coefficient. We still need to do that, 0.2. And we could go plus 0.2. Any questions on that there? So in this case, one of the first assumptions that we make is we're going to assume all the metal gets used up because of the really large value of K in this case. That means when we get to equilibrium, I feel like I made an icy almost. This is going to be 0 here. That's going to be 1.2 minus 4 times 0.2. And that's going to give us here 0.4. And this is going to be 0.2 here. Any questions on that? Now, you might be asking yourself, the question wants to know how much copper ion is present at equilibrium. And clearly we just zeroed it out, which means that wouldn't be much of a question at this point. So the second part of the assumption that we do here is, although we assume that almost 100% of all of that copper in this case is going to end up in that complex ion, it is still a reversible reaction, which means even though almost all of it is heading in this direction, because it's a reversible reaction, there should be a little bit of it heading back the other way. So what's going to happen is we should assume that we will end up with a really small amount of free metal still floating around that solution, but we will still have something there, but it should be really, really small. So let's see how we could get to that. We could get to that by, although we zeroed out the metal here, we could then go back and basically say, we actually do want to kind of solve for it at this point and see how much of it is still free in that solution. That is where our KF expression is going to come into play. We're going to take our KF, which is 5 times 10 to the 13. We're going to put in our values here at equilibrium, 0.2 for our product. Our copper 2 is what we're looking for. And our NH3 is 0.4, which we still need to take to the 4th power. We're going to solve for copper 2, which basically means these two guys are going to switch places. So we're going to multiply the copper 2 to the other side. And that will give us 0.2 up on top, 5 times 10 to the 13 on the bottom, and our 0.4 to the 4th also on the bottom here. As this guy gets divided, this guy gets multiplied to the other side. So they basically just kind of switch places. That's going to give us now 0.2 divided by 5 to the 13 divided by 0.4 to the 4th. Going to give us a 1.6 times 10 to the minus 13 molar as the free copper 2 concentration moving around in that solution. Is that a large number or a small number? That's like a super small number, which basically means that our first assumption is correct. Pretty much all of that copper is in the complex ion. There's just like a smidge. If you go out like 13 zeros or 12 zeros there, you'll find something, but not very much of it. It's pretty much all in there. So those are the two assumptions that we make in these type of problems. We assume all the metal gets used up. So that should always be really like the change part of these tables. And the second assumption is we assume that the free metal ion should be a really small number, which obviously it was in this particular case. If you ended up with a copper 2 concentration with a really large value, you did something wrong in this situation. Because of that KF value being so large, it basically turns this reversible reaction into kind of like a one-way street towards the products, but it is still a reversible reaction, which means you'll just get a super small amount of it will come back the other way and still be free. Any questions on that calculation there? All right, I did one. Why don't you try one and see how you do here? All right. So here we're going to do this one. This is actually a stepwise dissociation or stepwise fashion here. We want to calculate the concentration pretty much of everybody when we mix together 150 milliliters of 1 times 10 to the minus 3 molar silver nitrate with 200 milliliters of 5 molar Na2S2O3. Here, we're obviously not keeping everybody's volume constant. So give it a go, see what you come up with. Basically, we want to find everybody's concentration and see what you end up with here. Okay, so let's take a look at this one, see what's going on. So in this particular case, they gave us sort of our stepwise formation here, our complex ion. So we may want to perhaps get the overall reaction that's happening. And again, we could kind of simply do that by adding both of these guys together. In this case, that guy's going to go away, I believe. And that should be it. This will give us really an overall of a silver ion plus a couple of our S2O3 2 minuses, making our complex ion here of our silver with a couple of those guys attached in this case. We can write our KF for this if you like, which is our product here. Over our reactants. And once again, here we do need to, in this particular one here, square that guy there. We actually don't have the KF value given to us, but since we added both of these together, if we wanted to get a value for it, we could get the KF value by multiplying those guys together. 7.4 times 10 to the 8 times 3.9 to the 4. And that will get us there 7.4 to the 8 times 3.9 to the 4. Going to give us, we'll call it 2.9 to the 13 in this case. First off, any questions so far on that there? All right. So since we are looking here at the overall reaction, which might be helpful since, frankly, in this case, we want to really find everybody's concentration along the way. We probably want the concentration of those guys after they're mixed together. So the silver here is going to come from the silver nitrate, right? Is the source of the silver. And again, this is going to be a M1V1 equals M2V2 situation to get us our concentration when they're mixed. So initially here, we got 150 milliliters of our silver nitrate, 1 times 10 to the minus 3 molar equals M2. Our total volume is 150 plus 200. So that is going to give us a total volume of 350 milliliters, which will be our V2 in this case. And if we solve for M2 for our silver, that's going to be 150 times 1 to the minus 3 divided by a 350. Going to get us here, I'll go 4.29 times 10 to the, looks like minus 4 molar. This guy right here is going to be our source of the S2O3 2 minus. So to do that, we're going to do a similar calculation. Again, M1 in this case is going to be 5 molar. V1 is going to be 200 milliliters. M2 is what we're looking for, and we have the same 350 total volume here. Our M2, which will be our concentration of our S2O3, will be 2.86 molar here. Any questions on either of those calculations there? All right, so since I'm looking for really everybody's concentration, I'm going to actually just start with the overall reaction and see where we end up. So I'm going to go to the next page here and start with that overall reaction. So we again had silver plus a couple of these guys here. And that gave us our silver plus a couple of these guys here. All right, so using our concentrations that we just calculated on the previous page, our silver was 4.29 to the minus 4. Our S2O3 was 2.86 in this case. So that's what we're going to use for our initial. And again, we're going to go with 0 here. Once again, this is a KF and obviously a complex ion being formed. And as we saw, since we actually did calculate the KF value here, I think it was to the 13th, was it, or something like that? So that is, again, a really large value. So we can make our assumption that we did in the previous problem that all of that metal in this case, which is the silver, should pretty much head this way and get used up. So once again here, we're going to use the metal as our change. So this is going to be minus 4.29 times 10 to the minus 4. This will be minus 2 times 4.29 times 10 to the minus 4. That 2 is like 2x. So again, you got to make sure you take that into account as you're doing it. And over here will be plus 4.29 times 10 to the minus 4. That means at equilibrium here, we have nothing of this guy. We got 2.86 minus 2 times 4.29 to the minus 4. That's going to get us, surprisingly enough, a 2.86. And that's going to give us 4.29 times 10 to the minus 4. Any questions on that ice table? All right, so off of the first ice table, we actually have answers to 2 of the questions we're looking for. We just figured out the concentration of the S2O32 minus at equilibrium, which is 2.86 molar still. We also figured out the concentration of our complex ion at equilibrium by using the overall reaction here, an ice table, which is 4.29 times 10 to the minus 4 molar. So we found this guy's concentration. We also found this guy's concentration. There are 2 things that we're still looking to find. We are looking to find the concentration of this guy and also of silver. So it really doesn't matter really which one you go for first. But what I'm going to actually do in this case is, since they gave us the stepwise formation here, I'm going to actually use the individual steps to figure out all of everybody's concentrations. So with that being said, I could actually use right at this point, after I did the first ice table here, I have this guy's concentration and I have this guy's concentration, which means I could use just the second step here to find the concentration of the AgS2O3 minus. And that's what I'm going to do. So I'm going to use, in this case, because they gave it to me like that, so why not? I'm going to use the K2 here, which, by the way, if I write the expression for K2 is the silver complex ion here divided by this guy here. which is what we're looking for. And this guy here. And that equals the K2 value that was given to us there, which is 3.9 times 10 to the fourth. Now I'm going to answer the question that everybody asks at this point, which is, why did I not square the S2O3 in this case? Because that equilibrium is based off of not the overall reaction, right? It is based off of the second step where it has no coefficient. So that is what the K value we're using for the second step only. And there is no 2 in that case, and that's why we did not square it. Now, if we were going to do something with the overall reaction, we would need to square it, but in this case we don't because we're just using the bottom step here, okay? So the reason we're using the bottom step is I have everything but this guy. So if I put my numbers in from above, I have 4.29 times 10 to the minus 4 divided by this sort of intermediate, which is what we're looking to solve for its concentration. And we do have the S2O3, which is 2.86. Once again, if we mathematically solve for that, these two guys are going to switch places. We're going to multiply the guy on the bottom to the other side, divide the guy on the left back over. And that will give us the concentration of this guy here, which is what we're looking for. And the question will equal 4.29 times 10 to the minus 4 divided by 3.9 times 10 to the 4 and 2.86. That is now going to give me 4.29 to the minus 4 divided by 3.9 to the 4 and divided by 2.86. That is going to get me a lot of zeros there. I have mine in scientific notation, so I got 3.8 times 10 to the minus 9 molar. If you do not have a scientific notation, you may have a bunch of zeros and a 4 at the end as your calculator runs out of room, which is okay as well. Any questions on that? So by using the second step here, which is an equilibrium reaction, we're able to find sort of this intermediate concentration. Now, since I'm using step by step here, I'm going to actually now use the first step because what I just solved for was this guy, which means the only thing I'm missing from the first step is the silver, which I'm looking for. So I will now go and use the first step here to figure out my silver's concentration. And if I do that, let's do it right there, I think. Using our first step, which is our K1, that will equal the guy we just solved for, divided by our silver concentration, which is what we're looking for, and our S2O3 2 minus, and that will equal our K1 value of 7.4 to the 8. Once again, here we are writing our equilibrium expression based on just the first step here, not the overall reaction. So just the first step, which is again why there's no squaring of anything. And we could do that because now we have all those numbers. So that means that we will have 7.4 times 10 to the 8 is equal to 3.8 times 10 to the minus 9, which is what we just solved for, divided by the silver concentration, which is what we're looking for, and our 2.86 here molar. Once again, when you rearrange this, these two guys are actually going to switch places, and that will get us that the silver in this case equals 3.8 times 10 to the minus 9 divided by 7.4 times 10 to the 8 and 2.86. Whoop. Here we go. Divided 7.4 to the 8 and divided by 2.86, 1.8 times 10 to the minus 18 molar will be our silver concentration in this case. We made the assumption that all of the silver, right, should get used up in the complex ion. The second part of that assumption is the amount of silver should be a large number or a small number. Should be a small number, and I would say that qualifies as a very small number in this case. Again, essentially, all of that silver is getting used up into that complex ion. There's like a smidge of it still freely floating. Any questions on that there? Now, I did it step by step here to show you that because each of these steps are equilibrium equations, you could do it step by step. If you wanted to, you could have, at the end of the first ice table there, found the silver concentration, and it will come out the same by using the overall K value. So just to kind of show you that there, the K value that we had was 2.9 to the 13. So the KF for this overall one was 2.9 times 10 to the 13. And I'm just going to erase the blue part in the middle there, I think, and I'll do it right there. We can see it since we have the numbers on this page. Let's just get rid of that here. So if we wanted to, at the very beginning here, we could have attacked the silver from the overall equation using the KF value for that overall reaction. So if we did that, just like we did on the previous problem, what we would have done was come back here and go, okay, I now want to make this X and solve for it. And we would use the KF for the overall reaction, which would be our complex ion divided by our silver. And now, because we are using the overall reaction here, we do need to square it because of the 2 that's in the overall equation here. And this will equal our 2.9 times 10 to the 13. Once again, these two guys are going to basically switch places, and the silver concentration will equal our 4.29 times 10 to the minus 4, which is this guy's concentration for the first table, divided by the KF, which would be 2.9 times 10 to the 13, and divided by our S2O3, which is 2.86. That once again, we do need to square in this case because we're using the overall K value and the overall reaction. And that would get us, if I didn't screw up here, hopefully, we'll see. Looky there, 1.8 times 10 to the minus 18 molar. Yeah. Which obviously is the same number that we got here. At this point, once you would have the silver, you could have went into K1 and solved for the intermediate and got the intermediate that way as well. So there are multiple ways you could do it. They're all equilibrium equations. They're all equilibrium sort of expressions. So you could pop equilibrium values into any of these things. You just got to make sure you're using obviously the correct K value with the correct expression when you solve for it. Any questions on that there? All right, fun with K's here. Here we go. One more fun with K's to finish it out, I think. In this case, we want to calculate the molar solubility of silver chloride in 1 molar ammonia solution. So here we have 2 reactions. We have the silver chloride breaking apart into our silver ion and our chloride ion. And that obviously is a KSP type expression like we've been talking about, 1.6 to the minus 10. We then have our silver ion and our ammonia making a complex ion, which is a KF of 1.5 times 10 to the 7. So if we want to see what's going on overall here, we could add these guys together. So if we add these guys together, dare I say the silver actually cancels out. And that leaves us that we have some silver chloride where we want to add a little bit of ammonia to it to make this complex ion with silver and ammonia and a little chloride ion floating around. This should look familiar to you because you actually did this one right here in person in group 1, at the very end of group 1, after you added ammonia to your solid, right? And you had your silver disappear, right? And it didn't actually disappear. It disappeared into this guy right here, is basically where it went. So we could get the overall K value here by taking the KSP and times it by the KF. Can I do that if this one's a KSP and one's a KF? I can. They're all equilibrium constants. It doesn't really matter what the little subscript is. You can multiply them together. Kind of same idea where we did Ka times Kb equals Kw. It doesn't really matter. They're all equilibrium. So if we do that here in this case, that is a 1.6 to the minus 10 times 1.5 to the 7, 2.4 to the minus 3 in this case. All right, so in this case, we're actually looking for the molar solubility of silver chloride in ammonia. So this is actually going to be more of a KSP type of table we're going to do here to figure out the molar solubility. Also, we got rid of the ion floating around there, the metal ion, so we're not going to do a KF type calculation in this case. So if we roll through here, and once again, put this together, we will have our silver chloride plus our 2 ammonias, again going to our complex ion, and a little chloride action going there. And the K that we just got there was 2.4 times 10 to the minus 3. In this particular case, the only piece of information we're given is we're going to toss in there 1 molar of ammonia. So why not put 1 molar here? Sounds good. We'll do a little zero action happening here. We're then going to do our change, which this is going to be minus 2s, right? Because of the coefficient in front of the ammonia. And it is on the left-hand side. This is going to be plus s and plus s in this case. That means that when we reach equilibrium here, we will have 1.0 minus 2s. We will have s, maybe s, and s in this case. Any questions on the ice table? It is essentially like a KSP table, except in this case, we actually got somebody on the left-hand side here because we comboed a couple of reactions together. This is going to go into our K expression, which will be our products, which is our complex ion, times our chloride, divided by our ammonia, which we also need to square in this case. And that's going to equal our 2.4 times 10 to the minus 3. In this case here, we do not include the silver chloride, right? Because it is a solid. So putting our values in will give us s squared up on top divided by 1.0 minus 2s squared is equal to 2.4 times 10 to the minus 3. That is a what? That is a perfect square. So just some big old square roots on that thing would be a nice move. That's going to give us s on top. It will give us 1.0 minus 2s on the bottom. And we want to make sure we actually do take the square root there of our K value, which is 2.4 to the minus 3. That's going to give us we'll call it 9 times 10 to the minus 2. So in this case, we want to solve for s. So we're going to take what's on the bottom here and multiply it to the other side. That's going to give us s is equal to 4.9 times 10 to the minus 2 minus 2 times 4.9 to the minus 2. Going to give us 9.8 times 10 to the minus 2 s. Bringing our s back to the other way and adding it will give us basically 1 plus 9.8 to the minus 2. Gives us a 1.098s is equal to 4.9 times 10 to the minus 2. Finally, here dividing one last time the number back to the other side. 4.9 to the minus 2 divided by that answer, going to get us an S of 4. We'll call it 5 times 10 to the minus 2 molar. Any questions on that there? That is the molar solubility of silver chloride in ammonia. Yeah. Any question on any of those steps? So this is basically what you did in the end of group 1. Let's see if this is a big deal or not. So we have our molar solubility of our silver chloride in ammonia of basically 4.5 times 10 to the minus 2 molar. Now, if I take my silver chloride, which is 107.9 for the silver, plus 45 grams per mole for the chlorine, that gives me a molar mass for silver chloride of about 143.4 grams per mole. So if I take this is 4.5 times 10 to the minus 2 moles per liter of silver chloride, times it by the molar mass here of silver chloride from the periodic table. That gives me a solubility of silver chloride in ammonia of approximately 6.453 grams per liter of silver chloride in ammonia. Earlier in this chapter, we figured out the solubility of silver chloride in water, and it was 1.3 times 10 to the minus 5 moles per liter of silver chloride in water. If I multiply that by the molar mass of silver chloride in water, that gets me 1.3 to the minus 5 times 143.4. There we go, 143.4. There we go. About, we'll call it 0.0019 grams per liter. Yeah. Which one is it more soluble in this case? It is way more soluble in ammonia. That is why when you had your solid, when you did group 1 of silver chloride, and you added the ammonia to it along with your mercury, that is enough for like the ammonia being present to rip the silver out of the chloride's hands and go, I'm going to go join up with the ammonia and make this complex ion. Because of that really large value of Kf, it is enough to basically take the silver away from the chloride, and it will then go hook up with the ammonia and make that complex ion. And as you can see, much more soluble in ammonia, 6 grams versus like not even like 0.1 of a gram in 1,000 milliliters of water versus ammonia. That is also why when it disappeared, you went and added some nitric acid to it, right? When you added nitric acid to it, that's going to make it a lot more acidic, which is going to get rid of the ammonia presence. And that's going to free up the silver ion again to go find chloride, which is still floating around in that solution. And those guys are going to come together. And that is why your positive test for silver was the reformation of silver chloride at the end. Because when you made it really acidic at that point, when you added the nitric acid, you got rid of the ammonia, freed up the silver ion now back in the solution that can find the chloride. And since he has no choice of ammonia at this point, it's going to go back to the chloride, and you're going to see that white solid reappear. This explains what you actually saw when you did group 1. Any questions on that? Our complex ion formation. This is chapter 15.